Okay, we're in section 33 now, and this is the fundamental theorem calculus. We're going to make the problems a lot easier to deal with. However, I will point this out for some students, myself included, by the way, this might be, hard to get through. All right. Now, what I mean by that is the meaning of these things over here. It's easy to write it down, but where's this stuff coming from? We'll go through that. It's hard to present it, though, I'll be honest with you. We'll try to present it in a reasonable way. I do want to encourage you, though, read your textbooks. Your textbook probably give another reasonable approach to this. All right. You also may want to go to YouTube, watch that, whatever works for you. All right. I will say this, though. Most students get through this without understanding where it's coming from. We want to make some attempt to understand where things are coming from. And that's me going through these notes over here for you. So I'm going to go to the whiteboard now, and we'll look at it one step at a time. Firstly, introduce the fundamental theorem, and then try to talk about where it's coming from. And I'll visualize this as if I were studying notes. And we're trying to encourage you to do the same thing, by the way. Just give me a second to get my whiteboard on. Yeah, I think we're okay. So let's take a look at it. And I'm going to read it to you. And it says over here, FTC fundamental theorem calculus. And then they get this part 1, part 2 business. And let's take a look. So as I read this stuff over here, again, I encourage you to read it too. We're doing the FTC, fundamental theorem of calculus. It's given in 2 parts. Okay. It says if f is continuous on the interval on AB, that's an open interval, and ft equals f, the big F prime t. Well, we've been doing antiderivatives for some time now. So f is continuous on the closed interval. They claim that this thing over here, which we have had big problems computing, by the way, is really simple. That's what they're claiming. Now, certainly they can claim whatever they want, but I got to go through this. So some notation over here. What is it going to be? The integration of ft, provided ft is defined on the interval between a and b, continuous, that if we can find the antiderivative of f, little f with big F, and we evaluate it at b, the antiderivative at b, and we subtract away it evaluated a, we would get the answer. Incredible. All right. I want to claim about this notation over here. I'll write it on the side for you. When someone writes this down over here, they write down f of t, and then they put a bar here with a and b. This is shorthand. Whoops, sorry about this. This is shorthand for f of b minus f of a. You're going to see me do that quite often, the shorthand. All right. So let's take a look. FTC Part 2. Now, what do they say for FTC Part 2? They just simply say, hey, we could write it differently. So what they do? They wrote it differently. That's all they did. They took this thing over here. They write the same exact problem down. I mean, the same exact thing. The only difference now is they're changing this x here. You see that? That's all. Whoops, sorry about that. That's all they're changing. Now what are they going to do? They're going to do something that looks crazy. They're going to differentiate both sides. What are they differentiating? The left side and the right side. Now, differentiating interval to me looks crazy, but differentiating this side looks really simple to me. And why is that? I know the derivative, we've been doing this for some time now, of the antiderivative is just a little f. What's the other guy? What's derivative of f of a? Well, it's nothing to do with x. What's derivative is 0? All right. That's a pretty simple statement, by the way. So what does this allow us to do? Differentiate integrals now. All right. Okay. Let's make sense out of this. Making sense out of simple statements can be incredibly difficult to do. But I want to claim what they're doing over here. They're writing down something that may be best visualized. So I'm going to put this over here as a real simple visualization problem. And I'll put this over here, A to B, and then there's some function over here. I'll call it f of x. Right? I hope that's not a big deal for you. I can do that. And what are they going to do? They're going to do this g of b. This is what g of b is. It's the area under f of x, whether it's signed or not, doesn't matter to me, from a to b of f of x. That's all it is. All right, so see if it makes sense out of this. What do they tell me? I have to make sense out of it. They tell me g of x plus h. All right. So someone said, I wonder where that would be. Well, if I'm looking at this over here, I'm going to say, hopefully it's between A and B at this point, but let's just put this down over here. I'm going to put it over here. Right. So I'm going to say x plus h is somewhere between A and B to make sense out of this. And what would that area be? Well, it would be, let me just shade that in for you. It's this guy over here. That's that area right there. And then what do they do? Well, they take g of x away. I'm going to take h to be a positive number. And what's g of x going to look like? Well, that's going to be another area. It's going to be over here now. So now I start to realize what they're doing is they're only talking about this slice of rectangle over here. All right. Now, what do I know about that? I know the base of it is, let's see, x plus h minus x. So the base of it would be h, and the height of it would be some, value. Now, I don't know what value it's going to be. It could be f of x plus h. It could be f of some number in between there. I'm just going to say, if h is sufficiently small, I'm going to say the value of f of x, right over here. What am I doing? I'm doing the left endpoint. So I'm going to write a little bit differently now. I'm going to write it as g of x plus h minus g of x over h is approximately the same thing as f of x. All right, that's written right over here. By the way, h is not 0. We need a partition size. So I'm going to say h is greater than 0 for my picture. All right, now what are we going to do? We're going to take a look at the limit as h goes to 0 of this. And what does that give you? G prime. So what's g prime of x? Well, in the limit, it looks like f of x. Was I expecting that? I sure was. I was expecting that. And why is that? That's the way we've been checking our antiderivatives, just differentiating them. So I'm going to say that's a convincing argument. This is a convincing argument now that I was kind of expecting that these things would turn out to be functions that when differentiated, give me this back over here. We kind of just showed that for this small little picture over here. That's one convincing case, all right? It's convincing. All right, let's look at the next one. And as I do that, I want to go to the next page. I'm going to grab this guy here. I'm going to next page. I'm going to try to make sense out of this. By the way, when I say making sense out of something, not to everyone, it really takes tremendous effort to make sense out of things. All right. Some people say, I don't have the time for it. You're right about that. A lot of people don't have the time to make sense out of the world. All right. Let me push this over. So I'm going to basically talk about this now. And I like drawing pictures because they're easy for me. And I think I did this one before, didn't I? And let me just point out what I mean by that. I'll draw my picture again. And I'm going to say, I think we did this before, right? So there's some function starting at A. I'm going to say this is f of x over here. And I'm going to try to see what they said. And I know that we've defined this function a particular way. So it's going to be a to x now. And what's this thing over here? This is an area that's represented by g of x. By the way, when I say the area, signed area, could be above or below, it doesn't matter where it is. So then they claim over here is we could probably write something else down. And let me write down what they have written down now. They have g of x plus h minus g of x. Now I'm going to take x to be a positive number. I want to claim over here, if I did that, I'm going to say we're over here now. And this is going to be x plus h, right? So what I'm going to look at is I'm going to look at that, sort of like that little sliver over there and talk about it. All right. So I know what g of x is, and I'll write this down for you. That's going to be this. Whoops, I didn't mean to put that down. G of x, we've decided, was going to be a, it's written up on the very first statement, a to x f of t dt. What's the other guy going to be? A to x plus h f of t dt. All right. So we got this first line done now. Now someone can say, could I make sense out of the next one? I'm going to get my eraser out because I don't lose track of my thought. I'm pretty convinced that first line is good just by doing a visualization. I want to look at this next thing and see what they're saying for me to do. Let me erase this over. No, maybe I shouldn't erase that. So I'm going to, talk about what's happening over here. They're going from a to x and then x to x plus h. So that seems reasonable to me. What they're doing is they're taking it into pieces, two pieces. Let's talk about the two pieces are a to x, that's this piece over here. And then they go from x to x plus h. I hope you agree that's the same thing as this guy over here. So they just divided into two separate pieces. That's all they did. Now what do they notice? They notice that there's two identical integrations there. This guy and this guy will now disappear. So we're left off with. We're left off with this now. Let's write that down. So we're left off with g of x plus h minus g of x is going to be x to x plus h f of t dt. Again, h is not zero. What am I going to do now? I'm going to divide both sides by h because I want to get the derivative. So let's write this down. G of x plus h minus g of x over h is 1 over h integration x to x plus h f of t dt. This is the way I'd recommend when you read a textbook, you do this every step of the way. We got this down. There comes the next thing, which is going to be tough to think about, right? So what do they say? They say for h greater than 0, we know. How do we know? I don't know how we know. Oh, the extreme value theorem. They say we know some extreme value theorem. They say that f will take on a minimum, right? It'll take on a minimum and a maximum. Now they're saying the minimum is going to be f at some number u on the interval between x and x plus h. I don't know what that number is, but there's going to be some number on the interval between x and x plus h where the function would be minimal. That's u is going to be over here, u's on this interval, and so is v. So what's going to be v? It's where it takes on a maximum. I just don't know where they are. But I know between x and x plus h, there's a number u and a number v where the function f would take on a minimum and maximum. I know that. Or how do I know that? Well, extreme value theorem. I may not know where they are, but I know they're there. Continuous function, by the way. So what they do is they simply say, you know what? The area that's represented by that thing, well, the most it could be is m times the width of that thing. That's the maximum value. The least it could be is m times h of that thing. The m, by the way, because the width of its h. Then they say f of u is equal to m, and f of v is equal to big M. I got that written down. Makes sense to me. Then what do they do? Divide all sides by h. Where they get f of u is equal to, now we know why they did it. They're back over here. And what's that thing? This thing over here. So what do they get now? They take the limit as h goes to 0 of each side. This is squeeze theorem. What do we get? U goes to x, because if h is going to 0, that u is going towards x, and so is the v if h is going to 0. Where's this guy going? The derivative. This thing keeps popping back at us. What's popping back at us? What we've been doing all along is that when we found out the antiderivative, we just differentiate it and we get back the integrand. That's all we're doing. All right. So let me point out at the end of this thing, and I know it's tough. We're not asking you to explain this to anyone. We're not asking you on exams to explain it either. What we're asking is it's part of your education and it takes it's a really long road. I would recommend you read the textbook. See other ways people make sense out of the FTC. They need to make sense out of things to use them. By the way, that's not necessarily true. I drive a car and I don't need to make sense out of the car to drive the car, but I still drive a car. It would be nice if I could make more sense out of it, because I'll be honest, if it breaks down, I'm in trouble. So I'm going to say that we're going to be using the FTC for the most part to evaluate integrals. There are subtleties we're not appreciating over here, but the bottom line is we study more, we're going to see this is going to be a tough process. One of the toughest things we have to deal with, though, is can we find the antiderivative? And by the way, that is a very difficult statement. Can we find it? There are many integrals where we cannot find the antiderivative. In general, though, we have some nice techniques, which we will discuss in Calc 1 and in Calc 2 about how to find antiderivatives. I'd say the best way to find antiderivative is to know it. If not, we got limited techniques to find them. Other things I want to point out, computers are really good at finding antiderivatives, including numerical approximations. All right, we'll go to examples next. Hopefully this is not too difficult for you, though. As we go through examples, we're hoping that lecture becomes more concrete to you. But the bottom line is, I know this is a difficult section of the text. Thank you.